Hi. Yeah, I'm back, and there was a gap of 1 month or maybe two uh, between the last announcement I made that I would be reading research papers. Uh, I got busy with some family stuff and some stuff at work. But anyways, to start with, I'm kicking this session off with I'm recently reviewing uh, CMU's database lectures delivered by Andy Pavlou. I think they are for the master students studying there, and I was thinking that as I'm proceeding with the lectures, I can also make some YouTube videos out of it, just for revision purposes. And yeah, let's see. There are two lectures before this. I'm copying the slides from Andy, what he has delivered on the lectures. And there are two lectures for this lecture. This lecture is based on, it talks about file storage and how database files are actually presented out on disk, what different storage patterns there are. And before this, Andy discussed basic SQL in the past two lectures. The first lecture was the intro about the course, that how we are going to proceed and what different layers of the database system we are going to study and in what order. And the second lecture was about basic SQL, where he discussed that how uh, the paper written by Ted Cord, I guess, yes, I think so. I'm sorry if I'm pronouncing the name wrong, but I think the relational paper written by Ted Cord back in 1970, I guess, at IBM, how that led to the advent of these new relational database systems. So I'm going to skip those two lectures as the basic building blocks start from the third lecture, where he describes how the file formats are laid out on disk. So while I'll discuss this, my vision might be my camera is there, but I have my main screen on this side, so my vision might be I might not be looking into the camera, but who's watching? So let's get on with it. The database is Zoom. Okay. So what are we discussing here is we are discussing the basic building blocks of a disk-based database system. So there are different types of database systems. So there are in-memory stores which use the main memory, the DRAM, as their primary source of data. Be it Redis, and there is a database born out of India. What was it called? DiceDB. Arpit Behani, he made that thing back in 2022, I guess. But yeah, so those are in-memory stores which use the DRAM as their primary source of data storage, and they do not touch the disk. They might touch the disk in case if they need persistence, like in Redis, there is an option that you want to enable disk writes or not. So your in-memory data will be synced to the disk at given intervals. I think there is also an option that uh, given this particular number of keys, like let's say when my database touches 10,000 keys, I want to trigger a disk write for those. So I can specify the threshold that yes, for these, if my database touches these amount of keys, I can trigger a disk write. So throughout this lecture, like this series, Andy is also talking about disk-based systems. So yeah, that's what we'll be covering. So what disk-based database systems do is they assume that their primary source of data will be the disk, and they will just use the main memory as a caching for that main data that they'll be fetching from the disk. So during the whole designing of the database system, we'll have to keep in mind that we are not just dealing with the DRAM, which is byte addressable, that we can just address any byte in the DRAM, but we are also dealing with the disk, which is a block addressable system. Like I want to read some data out of disk, So I cannot just go about saying that I need this particular byte at this offset. I'll have to read in a block. Usually a block is like 512 bytes, or you can say 4 kilobytes. So I need to read a block and into memory, and then I need to get to that particular byte which I need to read. And back in the day when there were HDDs, there were sectors on the plates. Each sector was, I guess, about 512 bytes, but that also depended on the thing that how you lay out your file system on the disk. So yeah, let's get on with it. So yeah, that's enough talk about disk-based system. So yeah, what we'll be talking about is that we are using SSDs and HDDs as our primary storage location. So we'll have to look at how they perform, if I may. Like if we were talking about just in-memory systems, we would stop our journey right to this above system. Like if we were talking about let's say Redis without the persistence function, then we would just be talking about CPU registers, CPU caches, and DRAM. But we are discussing disk-based systems, so we'll be including SSDs and HDDs and network storage also. So network storage is a very fascinating topic. Recently, the cloud system has become very cheap and popular, and object stores are on fire. So, like people are building these database systems which treat the object stores in the cloud as their primary storage location. So, let's say I have S3 buckets, or let's say I have some bucket allocated on some cloud provider, and I'm just telling my database that yes, this is your primary data location, and you need to just go ahead and figure out what's out there on that particular data store. So what that gives us is, first of all, you'll have kind of an infinite storage, like you'll run out of money before you can run out of storage, I guess. And but that also introduces some latency problems, and yeah, that's a whole different discussion. So in this slide, what we are looking at is we are looking at a hierarchy where we are discussing that how different memory segments correspond to the cost in the market. So what we are talking about is that if you need a CPU that has a lot of registers, then you'll have to pay a lot of cost for that. But as you go down the hierarchy, like if I go down from CPU registers to the HDD, the cost relatively falls down. So SSDs and HDDs are not as expensive as DRAMs and CPUs with higher level of caches and like big caches and more number of registers. So although CPU registers are fast, but they are expensive. So, the ideal scenario would be that I have a CPU cache that is like, let's say, 4 gigabytes, and I never have to go to the SSD to read some data out of the SSD because SSD is slow. As we are looking at this, as we go down, the slowness increases, but as we go up, it becomes more expensive. So it's also written here that if we are moving up, it's faster, smaller, and expensive. So, the ideal scenario would be faster, bigger, and cheap. So that would be uh, assume a CPU cache of 4 gigabytes and you're getting it for the cost of SSD, let's say a Samsung SSD. That would be the ideal scenario if we were living in a perfect world. But yeah, but that's not the case. So, I mean, I heard Andy say about AMD CPU. They will sell you a CPU with that has 800 megabytes of RAM, which is a lot because back in the day they had CPUs which had like 4 kilobytes of RAM. Sorry, 4 kilobytes of caches, L3 caches. So I think I said 800 megabytes of RAM. I meant 800 megabytes of L3 cache. So yeah, Yeah, so this is our network, this is our storage system. So what we'll do is we'll read from HDDs and SSDs or network storage, and we will cache the data in the. Okay, so there might be a small cut in between because my battery ran out. So I think I might have to join these two videos. I'm not editing in edit like going all the way and editing like joining the two pieces. But yeah, so what I was saying was that we are going to treat SSDs and HDDs as our primary data source, and we'll be reading data from these sources, and we'll be using the DRAM as a cache. This is not working. Just a minute. Yes. So what we'll do is we'll be treating the DRAM as a cache for the data that will be coming from SSDs and the disks. And then we can also think about how what localities of like when we are designing the system, what locality do we want such that the CPU caches and the CPU registers can efficiently use that data. So let's say let's talk about spatial locality and what other localities there? Spatial locality. Yeah, the spatial locality is where two data pieces that are located close to each other are uh, have more tendency to be used together. So what you can do is the CPU caches can cache those two particular databases together. So whenever the CPU requests for that other piece, uh, it can be immediately served from the CPU cache. There is one more type of CPU caching, which type of locality which I'm forgetting. Just a second. Temporal, temporal locality. So temporal locality is basically a CPU instruction using the same piece of data again and again. So like I'm I'm using the same variable in a loop, or I'm accessing the same memory location again and again. So temporal and spatial locality, we can think of along the lines of that also while we are storing data. And the thing is that to be thinking of storing data, to be thinking of our caches being very good at caching, caching the relevant data, we'll have to start with the data we are storing in the SSDs, because that is the data that will be reading into the DRAM, and that will be the data that will be fed into the CPU caches. So if we have bad data alignment in the SSDs itself on the persistent store, then there is nothing that CPU caches can do. So like if you have, let's say, randomly spread random data spread across multiple blocks, and there is no sense of order, no sense of any order in that particular data, then there's nothing that CPU cache. You cannot leverage the CPU caches for localities, for exploiting CPU caches. So yeah, yeah. So another thing about this is the black line I drew. This this black line you can also see. Anything above this is volatile. So volatile, by volatile you mean is if I turn off my battery power, my laptop, if I turn this off, then anything in the CPU caches, registers, and the DRAM will be wiped away. And anything above below that, SSDs, HDDs, and network stores, they are meant to be persistent. Uh, yes, but like you can lose SSDs all the time. So yeah, but it is a non-volatile store. Like if nothing goes wrong, then my SSD will contain the data. But anything above that, DRAMs and CPU caches and registers, they all are just volatile stores. And Another interesting thing Andy talked about was something known as Intel Optane. So that was an attempt to to blur this black line. So that was an attempt to provide a DRAM which had persistence capabilities. So you could treat that particular device as a DRAM to be byte addressable, but that could also persist some data. But I think it also said that that particular project was killed off by Intel. I think it was back in 2019 or 18. But yeah, it is dead. The project is dead. So yeah. But that could have been a game changer. So like whatever topics we are discussing right now, we are assuming that SSDs are separate things. But assume that like I always wonder that if Optane took off like ever, if the history was written differently, what impact would it have on existing systems? Like all the storage engines assume that SSD is the primary store, but now you are telling a storage engine that you have a device that you have a persistent store as well, and which is also as fast as a DRAM. So, yeah, but yeah. Uh, so yeah, this is what we talked about. These three things are disk. That's the memory, and this is the CPU. So throughout these lectures, if we are saying memory, what do we mean by memory is the DRAM. And if we are saying disk, we are not specifying what kind of disk. It can be a SSD, it can be a HDD, it can be a network store. But yeah, just assume that if somebody is saying disk, that means it is a persistent store. So data won't just run off if you turn off the device. And the CPU contains the CPU register and CPU caches, basic CS 101. Okay, so for reference, so this was very interesting for me also when I was watching the lectures. For reference, when we are reading data from different places, okay, so my video might have been cut again. Okay, so what I was saying was this was a very interesting diagram for me. This was a reference between what time it takes for the CPU to extract data from different locations. So let's say my CPU has an instruction that tells the that needs a data point. So this diagram says that it's 1 nanosecond to fetch from the L1 cache, 4 nanoseconds to fetch from the L2 cache, and so on. So, for the human brain to think about nanoseconds is a bit difficult. So what Andy did was he converted that to seconds. So think about to just scale it out and for our brains to comprehend what it means. Like thinking in nanoseconds is still like if I look at this diagram, 100 nanoseconds is not much for me. So my brain thinks that 100 nanoseconds, yeah, reading from the DRAM is cheap. But when I convert it to seconds, and when I look at that reading from the DRAM is 100 seconds, 100 nanoseconds is approximately 100 seconds. So that's not actually the time for the CPU, but given that the CPUs operate on a very fast speed and like the speed of like our brains cannot comprehend that speed. So just to take a reference, just to take a understanding of what it is like for the CPU to be reading from different devices, we convert that to seconds. So reading from the DRAM is like 100 seconds, that's more than a minute. Uh, Reading from the SSD, that's 4 hours. So that would be like me traveling from here in a bus and going like 50 kilometers to read that particular data, and so on. So network storage is 1.5 years, and that's what I was talking about, the network latency that there was. So yeah, in an ideal world, as I said, reading from the caches would be very fast. So L3 cache is missing here, but I think L3 cache would be somewhere around 20 to 30 seconds. Uh, yeah, it would be somewhere around 20 to 30 seconds. Okay, so uh, the difference between DRAMs and SSDs are that is that the DRAM is volatile and the DRAM is byte addressable. So what do I mean by byte addressable is that uh, I can address any single byte in the whole RAM. So what I mean is if I have 4 gigabytes of RAM and I'm saying that I need the byte at 4 megabytes, then my CPU can just go and get me the data at the fourth megabyte offset. But that's not the case with the disk. The disk is block addressable. So what you do is uh, whole disk, let's say this is the disk, this will be divided into blocks. So if I have like let's say 256 gigabytes of disk, then it will be divided into blocks, and you can decide the block size when you write the file system to the disk. But uh, the one fact that I took away from this was the disk loves sequential access. So what I mean with by that is if you're reading data from the disk, and if that data piece is sequential, so that's block after block after block, then the disk will fetch it for you very quickly. Why? Because back in the day, if you think of if you have seen those spinning disk hard drives where a head would be spinning like this. Let's assume that this is the head and this is my platter. So to read off the disk, I would move this head to different position in the platter and read bytes off of it. So let's say I'm reading random blocks out of the disk. So what do my head will do is, let's say I'm reading from this particular location right now. So my head will be here and my disk would rotate and I'm reading that block. But now I'm saying that I need to fetch a block that is far away from this. So my head would move to that particular location and then it would start reading. Now, the time it takes from moving the head from this location to that location is still some time, right? And in case of the speeds that CPU operates on, it might be a couple of seconds or not seconds, let's say milliseconds, some milliseconds. And in computing terms, that's a lot. So let's say I'm reading sequential blocks. So what will I will do is I'll place my head once and then I will rotate my disk continuously because all my blocks are sequential. So all my blocks will be coming one after another and I'll be reading data very fast because I'm not moving the head of the uh, spindle. That's not the case with SSDs though, but still, as a rule of thumb, SSDs are also block based, and reading like reading sequential blocks is much gives you many benefits rather than just randomly reading blocks out of the disk. So yeah, in this slide, there are some metrics. Uh, this is the random. Wait a second. Yes. So this first metric is the random access metric, which says that when you're reading blocks randomly, it usually takes out about 80 to 100 uh, microseconds. Is that, I guess? Yes, microseconds. And when you're reading sequentially, it's much faster. So obviously the distribution might differ, that some reads are slower, but yeah, on an average, you will get much faster speed and much better performance using sequential reads and writes. So, what the rule of thumb we'll always carry with ourselves during this whole thing will be that sequential writes on disk are the best. We are not doing random writes, neither we are doing random reads. So, uh, that that brings me to my original point, right? That if you don't have any order on the disk, then you cannot expect the DRAM or the caches to perform very well. So you need to have some order on the disk so that when you are fetching data, you are not fetching a whole bunch of data from random different points, but you are being very picky about what you want to fetch from the disk. Okay, so there are some system design goals here. Allow the DBMS to manage databases that exceed the amount of memory available. Yeah, so when Andy was referring to this, he referred to virtual memory as well, because that's what we do in operating systems, right? We are giving the illusion of to a program that it has more. We are giving the illusion to a program that it has more memory than that is actually available. So that is what virtual memory is all about, and we'll be implementing some portion of that, like something that is similar to that in our database management system by the help of something called as a buffer pool. So what we'll do is we'll bring in pages from the disk into the buffer pool that will be in the DRAM, and once we have all those pages in the buffer pool, then we'll just run some page replacement algorithm to figure out that if you want to free a slot, then which page to evict. That is how virtual memory works in operating systems as well, that you're bringing in pages and you have loaded so many programs that your physical memory cannot hold as many pages as you have loaded. So what happens is that your operating system just starts writing out pages to the disk, and when you context switch to the programs that you need, and if the pages to of that particular program are not in memory, then the operating system will fetch those pages from the DRAM, sorry, from the disk itself to the main memory. So this, yeah. So what we have is reading right into this is expenses, so it must be managed carefully to avoid RAS stalls and performance degradation. Obviously, reading to right, going back to this, reading anything down below is in hours. So yeah, we'll be avoiding writing to disk or reading from disk at all cost. But we are a disk-based database management system, so disk is our primary source. So we'll have to read at some point and we'll have to write at some point. But we'll just be very careful that we'll keep that particular the read and writes to the minimal. Uh, so yeah, I'm tired. Just give me a second. Random access on disk is usually much slower than sequential access, so DBMS will want to maximize sequential access. We talked about this. So this is what we are talking about. Wait a second. Let's move it right here. So this is what we are talking about. This is our disk. So what is a database? It's nothing, but it's just a bunch of files on disk, which normal humans, the human eye, or any random program cannot figure out what actually data is contained in that. Like if you hex dump, like object dump or hex dump the database files, you'll see bits and pieces of the data available, but you cannot make sense out of what data is lying to which tuple and which how many tuples there are. So database management system is nothing but a special software that writes specific files to the disk and then reads those files efficiently so that you can make sense out of the data that is contained in those files. So, yep. So what we'll do is we'll start studying how the whole system works. The storage, I should have shown you that diagram first. Hold on. Uh, this guy. So if we look carefully, the database system is built out of different layers. So what we are studying right now is the disk manager, this particular thing. So not even the disk manager, we're not studying the disk manager, but we are studying how the disk manager actually stores the data on the disk. What different file storage structures are there, and how tuples are laid out in the pages, and how files are stored on the disk. So that is somehow related to the disk manager. So what disk manager does is it reads and writes, and then it feeds those reads to buffer pool. Buffer pool is nothing but a cache, the DRAM cache we talked about, that will be caching data that we read from the disk to the DRAM. DRAM has this specific data structure called as a buffer pool, which will manage those pages that we read from disk. And starting from the buffer pool, we'll just forward the buffer pool will have raw bytes in it, And then access methods will be some functions that will make sense out of the pages lying on the buffer pool. And then we proceed forward that yeah, what query was given, and we are fetching the results from the buffer pool. We read raw bytes, then access method made sense out of those raw bytes. And then we have, if we have some join operations or we have some filtering operations, and that's how the whole pipeline flows. So this will be, let's say you have some select query. The select query will flow like this, reading from the disk manager to the buffer pool to access methods. And then we some at some later stage we throw the output to the user. Let's say we have an update query or the insert or an upsert. So what we'll do is the flow will go like this, that the query will tell that I need to modify this particular page, and the disk manager will bring that page into the buffer pool and modify that page. And then the disk manager will again write it out to disk at some particular point. We'll get there. Yeah, so let's get back to that. So this. So assume, so as I said, database is nothing but files on disk. So what you do is you have data and you just throw it out in a custom file format to a bunch of files on disk. And you're not bypassing the OS file system. The file system that lies on disk is still being used. Like when I'm storing these files, I'm using the file system itself. So I'm not bypassing the file system. Okay, so now the question is, how does the database management system store these files? So it can be one file for the whole DBMS. That's how SQLite and DuckDB I think works. DuckDB and my SQLite, they only have one file and they can store multiple tables, multiple databases, multiple versions of those databases in that particular one file. And but you can also design a system where you have multiple directories and multiple files, and you can have one file for each table, one file for each database, and it all depends on the use case, like what kind of system you have in your mind. So yeah, what we'll refer to is each file, one second. Huh. So each file will be divided into pages. So let's say I have a file, a database file. No, let's take this example. This is a database file. This whole thing is a database file. I'll just call it as db, wait, mydb.db. So this is my database file. What are pages? Pages are nothing but the whole file broken into small pieces. Small pieces can be defined like you can have 4 kilobytes of pages, then you can have 8 kilobyte of pages, and then you can have 16 kilobyte of pages. It all depends on what kind of database system are you implementing. So let's say you are you're designing a system that is read heavy. So what you'll do in read heavy system is you'll maximize your page size. Why? Because in one page read, I can fetch more data if my system is read heavy. If my database is write heavy, then I'll prefer that I break this whole file into smaller chunks. Why? Because then let's say I need to update 10 bytes in a page. But if my page size is 2 megabytes, then just to update that 10 bytes, I'll have to fetch the whole 2 megabytes, update those 10 bytes, and then write that 2 megabyte block out to the disk again. So that would be wasteful. So in a read heavy system, you'd prefer that your pages are smaller in size, let's say 4 kilobytes or 8 kilobytes. And in a read heavy system, you'll have large pages, let's say 2 megabytes or 3 megabytes. That's what column stores do. Column stores usually have like 8 megabyte pages. Uh, Column stores are like, we'll get to that also. But yeah, no one's watching this, so who cares? But okay, so we discussed that a database file lives on the disk and it is divided into pages, and there is a page directory which tells me that what data is contained in which page. So, so what I'll do is whenever I'm reading from a database file, I'll bring this page directory into the buffer pool. What is a buffer pool now? Let's talk about buffer pool for a bit. Let's say there is some execution engine which is lying above the whole system, and it is telling my buffer pool that I need to get page 2. We are going to ignore the fact that how it got to page 2, but it's telling my buffer pool that I need to get page 2. So what buffer pool will do is bring this page directory into the buffer pool first, read this page directory, and then it will figure out that yes, the page number 2 is lying at this offset in this file. So let's say I have uh, let's say my pages are 4 kilobytes and I have a file that is let's say 400 kilobytes. So the very first page will be my page directory. I'll bring that in. Then I'll figure out that my page 2 uh, a page directory will contain a bunch of information like what page sizes are we following on this file, etc. And then I can just figure out that in order to read page 2, I'll have to jump to this particular offset. And then I'll just read the page 2 into the buffer pool. So once I have this directory in, and when I figure out that where to fetch page 2, I'll just read page 2 into the other block, page 2. And then I will pass that particular thing back to the execution engine, which will just perform its calculation. Like it will read raw bytes out of that page, and then it will make sense that how do I stitch tuples together. But we don't care about the execution engine right now. So I think Andy must have shown in some slides. Yeah. So in this step, as you can see, directory is being fetched into the buffer pool. And once directory is there, then I know that how do I want to read the whole database file. So that's what I did. I got the directory, then I figured out how do I get to page 2, and then I read page 2 into the buffer pool, and then I passed a pointer back to the execution engine that yeah, this is your page 2, and you can just interpret the layout in the page 2. And let's say, so in this particular example, this arrow shows that there's an update going out to the page 2. So what my execution, let's say we had some update query and my execution just updated that particular page. And at some point, my buffered pool will just write that page back out to disk. At what point that we are not seeing. And because that involves a couple of things like write ahead logging and other things that we'll get to. But yeah, this is basically how the system works. And Andy has also told that yeah. So like lecture 3, 5, and 6, like the slides I'll be covering in the next part of this video, or like of this series, will be talking about how database file is laid out and on the lower level how database files actually look like. And yeah, in lecture 4 we'll be discussing the same, like we'll be discussing about database files. In lecture 4 we'll also be covering buffer pool. These are like basic uh, outlines of in what lecture we'll be covering what. So yeah, today, like in this particular lecture, in this particular slide, in these particular slides, we'll be covering how the database represents database as files on disk. Like, so if till now, if you have not understood anything, like I'm a bad teacher, by the way, but if you have not understood anything, the key takeaway you have to like the key takeaway is that database is nothing. Database management system is a software that just writes out your data to specific to very special files to disk. They are not like not very fancy files that will be separate from regular files from the of the operating system. They are regular files, but they're special to the database system. So if I look at those files with my raw eye, like if I open it in the text editor, I will not be able to read data. But my database management system software ensures that it will be able to read those files back and in a efficient way, like in such an efficient way that even if I'm storing gigabytes and petabytes of data, it will still be able to cope up with that. So yeah, that's what database management systems are all about actually. Just files on disk with special files on disk. They are more about that. That's a controversial statement. Okay, scrap that. I'm not saying that they are all about that, but it boils down to that particular thing that you are writing files to disk or some network storage, and then you are reading them back out, and just you're storing and reading such with such an efficiency that you term that software as a database management software. So yeah, this is file storage, which we'll be covering in the next part because I'm tired. Thank you.